Recording has started.
All right, let's move on. So the capacitance in the MOSFET. So you may wonder that here we have this RC, and we talk about the R is related to this W over L. How about the C? So what is this C we should use for the inverter? So we need to take a close look at the MOSFET structure to figure out the C, because previously the C is a lumped capacitance. Now we have to break up this lumped capacitance into the individual capacitors. So in the MOSFET structure, there are many capacitances here. So the first one, the primary capacitance is a CGC. So that is the gate to the channel. And you know this is the gate oxide. So you have the COX. But COX is, by definition, gate capacitance per unit area. So we need to multiply by the area to get the CGC. That is COX multiplied by the area of the gate. So what is the area of the gate? You have the W and you have the L. So the area of this gate is W times L. So that is the primary capacitance we have in the MOSFET structure. But there are many other capacitances as well. For example, here we have this junction capacitance, Cj. So this is a PN junction capacitance. Because this is MOS, so the source is N-type and the body is P-type. If you recall the lecture 7, we say that in the reverse bias condition, the PN junction is like a capacitor. There is a depletion region, and the depletion region's width will change according to the voltage. So it's like a capacitor with a variable distance between those two plates. So this junction capacitance will contribute to the overall capacitance of the MOSFET. So we have the CJSB, that is the junction capacitance between the source to body, and similarly CJDB between the drain and the body. So we have those two. And in addition, we have this COV, that is overlap capacitance between the gate to source and gate to drain. This COV is between gate to source and gate to drain. This is overlap capacitance. This is a secondary effect, but it's practical in the real devices, because when we do the fabrication, even though we define the gate area to be like this, so for example, this is a gate and this is oxide, and then we will do the source and drain doping, right? So we are going to inject the dopant, for example, phosphorus, into the silicon to dope the source and drain. So this source and drain will become N-type, heavily doped. Then this is ideal, but in the real fabrication, this transistor needs to go through a very high temperature annealing process to activate the dopant. So this process will drive the dopant to diffuse out. This high temperature will make those dopant movable. So this high temperature will make the PN junction more spread out into the panel. Then here there's overlap between the gate to the source and overlap between gate to the drain. So this is COV, overlap capacitance. This is relatively small, but it's still there, CGS and CGD, compared to the CGC. This is like typically like 10% compared to the primary cap from the gate to channel. The CGS is like 10% because here this diffusion is like 10% of the L. So those are the capacitances in the MOSFET. Any questions? And then let's consider what contributes to the CL, the load capacitance, to the output voltage here. So this is one inverter driving another inverter. And we look at the output for the first inverter. And previously, we just used a big CL to represent all the capacitance attached to this node. This is like lumped. But actually, there are many components here. So here, let's look at what contributes to this CL. If this is your total CL, actually, we can divide this into two major parts. So on the left-hand side, we see those are the C intrinsic, because those capacitances are intrinsic to the first inverter. And then on the right-hand side, we have C extrinsic. So let's look at the C intrinsic first. So basically, this node is a drain of both this NMOS and PMOS. If you recall the previous slide, on the drain side, you look at what capacitance attached to the drain. So you have this COV and you have this CJDB, the junction capacitance. So if you go back, so at this node, the CGD, gate to drain, this is a overlap capacitance. You will have that from both this Q1 and Q2. Q1 is NMOS, Q2 is PMOS, so you have the CGD1 and CGD2. Those are overlap capacitance. And then the CDB, so here this is body, this is body. So you have the CD between the drain and body, you have the junction capacitance, CDB1 and CDB2. Those are the junction. So you have those four capacitance attached to this node. You need to add those four. So here, this part is a C intrinsic. And here a special note is that in front of the CGD, we have a factor of 2. This is due to the so-called Miller effect. That is when we decouple a capacitance from the input to the output. If we decouple that into two parts, the input side and output side, then it will follow this Miller effect rule. So this K is like the gain of this input from V1 to V2. And in this inverter case, K is -1. So that means here both input will become 2C and output will become 2C. K is -1. The gain is -1 for the inverter. And we're not going to discuss more details on this Miller effect because this is actually this is an important topic for the analog circuit design. If you are designing like amplifier, and then this is very important. And here for the digital circuit, we were not going to discuss more details on this Miller effect. The conclusion is that here for the CGD, there's a factor of 2 in front of that. And then the extrinsic on the right hand side. Those capacitances are not part of the first inverter. Those are external or extrinsic. For example, first one is this C wire. This is because from this node of the first inverter's drain to the second inverter's gate, we need to go through the interconnect wires. That's metal 1, metal 2. So the wires will contribute to some parasitic capacitance. The wires, if you think about two wires, between the wires are the insulator. So it's like a plate and the insulator. It's like a capacitance. So the C wire is parasitic effect, and typically it's small for those local interconnects, but it can be large for global long interconnects. So we have C wire attached to this node. And then for the Q3 and Q4, this is the second stage of the inverter. And for CG3, so basically it's a sum of the gate capacitance of the Q3. You have CG here, so you will have the CGS, CGD. Those are the overlap capacitance, COV, and also the CG channel. So basically you have three capacitance to this CG3. Similarly, you have three capacitance for the CG4. So for the CG3, this is the gate to channel. And then we have the COV for the CGS and COV for the CGD. So those are the CG3. And similarly, you have that for CG4. So this is the second part, that is C extrinsic. And here in this slide is kind of complicated, so I don't require the detailed breakdown of those capacitance in this course. But at least you need to understand the capacitance attached to the output node has two major parts. One is intrinsic, that is associated with the capacitance of the first inverter by itself. And the second is C extrinsic, that is external to this first inverter, includes the wire and the capacitance from the second inverters. This is the minimal requirement you need to understand here. Of course, if you want to dig into the details, then here are the detailed breakdown of those capacitances. So any questions? But one question, for CDB2, why is it added even though its other end is not attached to the ground? CDB2. CDB2. Okay, so that's a good point. So to make it simple, when you look at this node, the other side, okay, is attached to VDD. But in the small signal perspective, the other side is ground. So I'm not sure if in the 2014 class it talk about the large signal analysis versus small signal analysis. So small signal, you only look at what is changing in the signal, right? Input is changing, output is changing, but the VDD and the real VDD and the real ground are stable. So in the small signal analysis for the analog circuit, all the constant voltage bias are treated as ground in the small signal analysis. Because when we talk about the capacitance, we are talking about the charging and discharging, those more like a small signal behavior. So all the constant voltage bias are treated as ground. So I don't know if this is covered in the 2040, but this is a concept in the analog circuit design. Okay. All right, so then let's look at one example to practice some of our approaches mentioned earlier. So this CMOS inverter delay, and the parameters of this inverter is given, like those numbers here. And here, to make it simple, we directly give you the C total, is this 6.25 femtofarad, and then calculate the TPHL. So in the homework or in the exam, I will specify use average current method or RC delay equivalence. RC equivalence. So here we specify use average current. Then how do we get the TPHL? So TPHL, if you recall the discussions earlier, so we have C total. This is non-CL, VDD divided by 2, and then I average. And this I average is this saturation plus this I child. So I will show you the solutions here. So the approach just mentioned is CVDD divided by 2 and I average. So we need to figure out what is I average. And initial current and final current. Initial is the saturation, final is the child. So let's plug in the saturation current equation, which is half mu n CoX W over Ln VDD minus VTN squared. And if you plug in the numbers from this question, you get 345 microamp. And the final current is this child current. And then child equation is mu n CoX W over Ln VDD minus VTN and then VDS. So the final point, the output voltage is half VDD. So that is your VDS. We have the half VDD here and the minus half VDD squared. So if you plug in the numbers, you get 296 microamp. So we take the average of those two. So then the average is like 320 microamp. Then we plug into here, you have the capacitance, like 6.25 femtofarad VDD. The power supply is given as well. In this case, 2.5 volts. And then you can calculate what is the TPHL. So the final numerical value is 24.6 picosecond. And pico, is 10 to minus 12. Similarly, you can get the TPLH. The approach is the same. The only difference is that you need to replace the MOS parameters with the PMOS parameters. So here you need to use mu P, W over LP, and then VTP, absolute value. So if you do that, then the TPLH will be 31.5 picosecond, and the average TP is the average of those two, will be like 28 picosecond. So in this case, you say that this is unmatched, and NMOS is stronger than PMOS. Why? The TPHL high to low transition, NMOS for high to low, and the high to low transition faster than low to high, PMOS. So faster, that means NMOS is stronger. NMOS pull down faster than PMOS pull up. So then you can conclude this NMOS is stronger than PMOS in this case. So I just skip all the derivations here, simply plug in the numbers. The most important thing is understand the approach here. Use this average current, and average current is the average of those two, saturation and child current. So any questions? Okay, then next we want to discuss one important issue, that is to do the gate sizing. So if we want to increase or decrease the delay, then we can play with the size of those transistors. For example, if we want to decrease the delay, then typically we need to size up the transistor. That means we increase the W over L. So here let's look at this inverter. As we discussed, you need to understand the two components for the capacitance. One is C intrinsic, one is C external. So if you remember here, we break up that into two parts, C internal or intrinsic and C extrinsic. So if we increase the transistor W over L by a factor of S, then the intrinsic capacitance here will increase by a factor of S. So this is C old, this is C new. Old means initial capacitance, new means after this sizing. Then the new capacitance will be S times C intrinsic, because all the capacitance here associated with the first inverter is proportional to the W. If you increase W over L, then those capacitance will increase accordingly. But the extrinsic cap has nothing to do with this size. We only increase size of factor for, let's say, for Q1 and Q2. So the extrinsic part will be unchanged. So C extrinsic still there. And then let's look at the RC equivalence. So the equivalent resistance, if we consider both NMOS and PMOS, will be average of the Rn and Rp. So the Tp will be 0.69. Again, this is from the previous derivation, this coefficient. And then Rc. Now if we increase the W over L, you know the resistance will decrease by this S factor. If you recall, the R is proportional to 1 over W over L. Then when you increase the size by S, this will decrease by S. So this is like R old, and this is old, this is new. Then we look at what is the new RC. So you have this 0.69, and this new R is this one, and new C is in this bracket. So this S cancel each other. So you have this RC intrinsic part unchanged. This part of the delay is intrinsic. And then the extrinsic part of the delay is reduced by S. So this is an important conclusion we want to draw. When you increase the size of the inverter by itself, the intrinsic part of the delay, no change. So intrinsic delay, no change. Why? Because the capacitance increased by S, resistance decreased by S, so cancel each other. Intrinsic delay, no change. But the extrinsic delay will scale by this 1 over S. Because extrinsic delay, the extrinsic capacitance no change, but resistance decreased by S. So the extrinsic part decreased by S. So overall, the delay reduces, but it's not to this factor of S. Then let's practice the conclusions we have into this example. So here this is like a follow-up of the previous example, where we have that C total to 6.25 femtofarad, and here we break down this intrinsic and extrinsic cap into those two. This is given for you, 2.9 versus 3.35. And then the delay, I think from the previous example here, is 28 picosecond. So that is the delay, TP, 28 picosecond. So now if we want to reduce the extrinsic part by a factor of 2, that means S equals to 2. So we need to increase the W over Ln and W over Lp of the first inverter by this factor of 2. But the question is, what is the new TP? So how do we approach this? So first of all, for this 28 picosecond, it has two components, intrinsic and extrinsic. So we need to break up that into the intrinsic and extrinsic. So out of this 28 picosecond, intrinsic part is 29 femtofarad out of 6.25 femtofarad. This is the intrinsic part of the delay. And then extrinsic part is 28 picosecond times this 3.35 out of 6.25. So this is extrinsic part. And then use our conclusions before. You increase the size by factor of 2. Intrinsic part no change. Extrinsic part reduced by this 2. So you should have half of that. So this is the new TP. And here is the solution. And so as we discussed, intrinsic part of delay is out of this 28 picosecond. If you do that, it's 13 picosecond. This part no change. And the extrinsic part out of 28, 15 picosecond. This part will reduce by 2, will become 7.5 picosecond. So the new delay will be 13 plus this 7.5. So it will be 20.5 picosecond. So this is to apply our conclusions earlier, that the intrinsic part no change, extrinsic part reduced by this factor of S, and in this case 2. So any questions?